So today we will shortly talk actually about each of these topics. First, I2C, another kind of communication protocol. We'll talk about the Lec5c project, quickly talk about DC motor and servo motor control. So this very last lab that you are going to work on in block 5 is actually on this I2C protocol, and I'll give you just a rough overview of what's going on here. So it's the same as two-wire interface. It's synonymous to one another. It allows up to 128 different devices that are now connected to two wires actually, and they're all connected to one another, by the way. So one of these devices will play the master, and the role of the master may even switch from one device to another device. We have two lines. One is a clock signal and the other one is a data line. So in order to be able to communicate to one another, we will give every single device a unique address, and if you have 128 of those, then 7 bits is exactly the right number of bits to be able to address that number of devices. So how does it work? Well, let's first talk about how to start communication. So the idea is that you have a clock signal, goes up and down, which is of course used to synchronize all the devices together. And next you also have this data line. So the idea is that when nobody uses the bus communication according to this protocol, your data line is actually high. And if you pull that low on a high clock cycle, then that indicates that you are ready to start communicating. So that's the start signal. And at some point you may have a stop signal, which is at the end of, say, a frame of data that you transmit. You go up on a clock signal, and you may then start again with something else. You may even have what they call a repeated start. So rather than at the end of a frame to say I'm done with transmitting what I wanted to transmit, I like to transmit another byte, and then you have a repeated start and you continue. Okay, so now let's have a quick look at what such a frame looks like. Now there are two things that you need to communicate. The first one is the address. Who do you like to communicate to? And once you have done that, you can start transmitting data. So let's first have a look at how you encapsulate the address. Well, we use 9 bits for them. First, we have the 7 address bits, starting from most significant to low significant bit. We want to indicate whether we want to do a read or a write. And next, we want the receiver, to whom we make either the write request or the listening request, we want that receiver device to acknowledge that that device is ready. Alright, so that's what's written out here. So there's such a frame is 9 bits long, and the master effectively, a device that assigns itself to a master because he wants to start communicating, then addresses what we call the slave. So the slave recognizes that it is being addressed, and at the end it should acknowledge. And how do you do that? Well, you pull in the data line to low in the 9th cycle. So look, we have we have this clock cycle, we have this data line, and the master is giving the address bits 1 and 1, and finally figures out whether it should be a read or a write. And then the master line will pull the data line high. So the master now knows if he sees that the data line is going to be pulled low because of the slave, then he knows that an acknowledgement is actually sent back in that way. Okay, so the master can then transmit a stop condition, like we're done, or a repeated start condition to initiate a new transmission. So what is happening now is that you would like to transmit a data packet, and a data packet is also containing 9 bits. We have 1 data byte, 8 bits, and also again an acknowledgement bit. We want to make sure to know that the data actually was received properly. So how is this being transmitted? We're going to actually transmit the most significant bit first, up to the least significant bit, and then according to the same principle that I just explained, we have an acknowledgement. So here we see it better explained in this particular part of the graph. We see that the transmitter is transmitting all that data, then pulls the data line high, and the receiver is listening and pulls the data line low in the for the ninth slot, in order to acknowledge that it had received indeed all the data and was listening carefully to what was going on over the bus. So, well, then you can do, for example, repeated start or a next data byte and so forth, or you can just stop. And one question you may have now is, well, wait a minute, what if multiple devices may want to start transmitting something? So, like 2 devices say, okay, I'm the master, I'm going to start. So how can you figure out who is winning to then in the end start transmitting a data byte? So here it is. So we need what we call I2 bus arbitration, because I may have 2 devices who self-assign themselves to be the master, say a master A and a master B, and they both say, I want to start. Okay, so then what do they start with? They start with transmitting address bits. And for example, for master A, he wants to transmit say 0 and then all ones, while the master B would like to transmit some zeros and then some ones and then some zeros again. And it actually continues over here, so we have a whole bunch of address bits. But the point is that master B, because he pulls the address line low, the address line will be low also when master A has transmitted a logical high or a high voltage. So what does that mean? Master A is not just transmitting stuff, master A is also listening to the data line, and notices that even though he pulls this line to high, he reads a low. So that means that he now knows that he has lost the arbitration and that some other node is actually at the same moment in time started a communication. So that means that he stops and he leaves it up to the other node, who then finishes all the address bytes and now can start data transmission. So that's how that works. Now, of course, very unlikely though, but you could have the situation that master A and B want to actually write or read from actually the same slave device. In that case, these particular bits will be completely the same for the address. Then of course you start writing data and you will find out whether you lose the arbitration if the data that you transmit is not what you see over the address line. Again, if you say want to transmit a 1 but you see a 0, then you know that this other master is actually in charge and happened to also communicate to the same slave with up to that moment the same data bits, but then you lose the arbitration. Now of course if they transmit the same byte, then that could lead to the situation, and even after repeated starts when you transmit more and more bytes, very unlikely, but suppose it would be the case, that it would be in the end leading to a situation both master A and B actually think they communicated that particular sequence of data bits to the slave. Well, when you are a system designer, then you should of course make sure, if it is important, that the data originates from master A or master B, if that's important to you, that you then need to put in a protocol step of communication that verifies that. But if not, then it doesn't matter, because the slave did receive whatever sequence of data bits it really had to receive. Alright, so in this particular situation we now see that we have a protocol in which you literally start transmitting both masters, and at some point you will figure out who is winning the game in a way, so the arbitration, and the sequence of transmission is really one in which we first start off with all the address bits, and whether we want to do a read-write, an acknowledgement sent back, and then you continue with data bits with acknowledgement sent back, and you will continue with repeated starts until you actually stop it. And I think I've put that somewhere. Is it, oops, what am I doing? Is it somewhere over here? Over here. The stop condition is by putting the SDA high at the 9th slot over here. So then you can stop. So anyway, so this is the structure of I2C. So what you're going to do is you're going to have a look at the data sheet. You're going to work with the assignments to program this protocol and then communicate. Alright, so let's move forward with the final part of this course, which is the Redbot project. So far, so in block 5 I leave you a lot more independent in many ways. You ought to look a lot more to the data sheet, figure out what's going on there, and then work with these communication protocols. But for the Redbot projects, you're really on your own. We will give you the actual Redbot car, each individually, and you will be programming a line follower. So the idea is that we will have a board with just a black tape, actually something like this, just going around in a sort of a circular shape, and you need to follow this. So you will build a line follower. So what do you have at your disposal? Well, obviously you need to you have motors, because you need to go forward with your robot, and you also need to you also need to steer, and at the same time you want to receive information about that black line. You do that through these IR sensors to receive information about whether you should go more to the right or to the left in order to follow that black line. So this is effectively what we're doing. So based on the IR sensor input, the Redbot needs to move along a line, a black electrical tape. What kind of functions are we going to implement? Well, you will need ADC, PWM. We will talk about it a bit for the motor and the H bits here. A GPIO, you have a LED that you will program. You have a UART because you want to get some information out of the car later on, and you want to connect to it and you get some information back from it. So this is a very rough description. After Thanksgiving I will give a much more detailed description with again in the form of an independent laboratory with several tasks. Okay, so we need to understand a few things in order to be able to do this. So the first that I would like to talk about is probably a recap for you, is PID control. So you probably have seen this elsewhere. Proportional integral derivative controller, and it's a general mechanism. So I'm not saying that you should do what I'm now going to tell you, by the way, but let's for now assume that on top of your car you have 3 infrared sensors, by the way, but let's suppose you only use the middle one, so one of them. And you could potentially reason about following the line as something like, I'm going to measure the amount of blackness that I actually detect. So, well, what is the maximum possible blackness measured by the line sensor? That's what I see, actually. what I could potentially see. So I'm going to normalize my measurement. So if I'm right on the black line, I want to figure out how much blackness do I actually see. So I need to somehow calibrate my sensors, right? So I do that, so that one sensor. So the difference with respect to what I actually measure in terms of blackness may give me some information about whether I need to go to the left or the right. Well, in this particular case, I do not know, because clearly if I only use one sensor, then I do not know whether I should go to the left or to the right. But let's assume for a moment that to explain this concept, that we have sort of an error signal, right? That's the difference between what I would like to see, which is that I'm right on top of the black tape, versus that I'm actually a little bit off, which is what I actually measure. So what do I do? Now I need to correct the rotation speed, so I need to go into the right direction. And how do I do this? Well, there are usually three terms that you pull into this equation. One is that I look at what I measure right now. Okay, so that plays a role with some kind of constant that I set. I can calibrate that. I look at this integral that looks at the past from 0 to t, which is really the amount of rotations added together in this particular case, or this blackness that I've measured together, and that may play a role as well. And finally, if I look at et as a function over t, I can have a look at its derivative and see, well, maybe I should dampen that a little bit, for example. So I have a derivative term that can help me to not start steering very much into one direction, but smoothing it out a little bit more, because I do know that they're building a line follower, so I do not need to go all the way overboard. So this is a continuous function here, written like this, but obviously you can just allocate just a digital time axis, right? So rather than thinking about t, you can simply think about t equals 0, that's the 0th iteration, the first iteration, the second, 3, 4. So how would you write out a derivative term? Well, at time t it would be simply e of t minus e of t minus 1, like what did I measure before, divided by 1, say, so that would be the derivative. In this particular case, I could just simply add the sum of all the previous errors that I have measured. In this particular case is what I currently measure. Now the question is, do you apply this type of mechanism in its full generality? Probably not, but you can at least start thinking about it this way, that there is this option for you to get into this particular framework. And if you do this, then you only need to estimate those particular constants to make sure that your car is sort of smoothly following that line. Now, as I said, it makes no sense to just look at one middle sensor, because if the blackness is reduced to say 50%, or is lit up to say 50% of what it should be, well, will I go to the left or to the right? Well, I could of course steer to the left and see, oh, that's the wrong direction, so quickly go back. So if you do that, if you use one sensor, you will see this wiggling going on, which may not exactly be what you want. But we have 3 line sensors, so you actually, if the black line is somewhere between, so if you have 3